Hey everyone. Well, I've seen through kind of like the agenda and realized that there probably is going to be a lot of talk about a bit of AI on blockchain, on LLMs. So I thought to kind of cover something that might not be that well observed, or the inner workings of something that most people might not know. So I think in this current kind of sharing session, I'd like to talk a bit more about computer vision, how it came about, and where are we today, and where we think it's going to go next. So what's computer vision? Well, it means a bunch of things these days, especially with generative AI. But I think what we are interested in this kind of sharing session is about building algorithms that allow for scene understanding, image understanding, and use it for other applications. So I think before we talk about how we got to where we are today in terms of computer vision, it's important to talk about why computer vision is hard. Because unlike many tabular data that many of you might have worked with, or sentences with LLMs, well, you can't strictly put things on a simple Excel spreadsheet with different columns that are structured and with an outcome which is probably like financial data, things like that, or reviews. Consider an image here I've just shown, which is potentially like an MRI scan. Say, for example, you're in the business of building tumor detecting models. Well, the computer doesn't exactly see what you think it sees, right? It sees different pixels and different pixel intensity values, and somehow we are instructing various methods to find out a particular tumor region. So it's really unstructured, and things can be anywhere, right? So before we talk about how we got to where we are today with vision transformers and CNNs, it's a little good to walk backwards and see how we got to the various key algorithms that develop those things today. Well, for computer vision alone, it didn't start in just the last few years. In fact, convolutional neural nets went all the way back in 1970s. But the computational requirements back then was too high to make it feasible. So we really started with various kind of pattern matching recognition systems. We went down to kind of edge detection. We went down to various kind of methods then and there. So let's dive into some of these things quickly. So on the very early 1970s portion, if you were to see banks using computer vision for detecting frauds in checks, a lot of those were circled around edge detection algorithms, right? What is about finding edges in foreground items like the little flower, houses, characters, numbers, things like that, signatures. So it was really an expensive process whereby you had to go through almost every single pixel of every image and then make a prediction on some of these items. The industry got smarter, however, with the introduction of things such as HOGs, right? Assume a particular dog or particular human is in a different corner of an image. How would you be able to write algorithms and pattern match those things? Well, for a while, HOG was the answer to many of these things, finding differences in gradients, differences in colors, and then using that to try to understand it as a smarter way for understanding edge detection, right? So as you can see, the industry has moved towards from something that is a bit more recursive to something that's going to be a bit with a reduced search space. But of course, that wasn't enough. The biggest problem with HOG was that if your item was of a different scale, if you were standing further away, or if you're standing in a different corner of the image, it might not be able to recognize you. So for many applications out there, including driving and things like that, and understanding scenes, SIFT, or rather scale-invariant feature transform, was one of the solutions for a period, right? Consider a picture like the mayo in the corner. That will be used as, for example, as a reference image. Researchers and research was focused around finding key points or key patterns. So instead of looking at the whole bottle of mayo, people are just looking for key features such as brand, the edges of a tomato, things like that, and mapping it back to a main image. As we can see, the search space for where things are have gotten smaller and smaller over time. But of course, we know that in the 2000s, with better compute and better drivers and things like that, CNNs has made its resurgence. CNNs present an idea whereby you could use a sliding or convolution filter and then kind of shrink down the image into its numerical constituents and predict things based on those items and numbers. CNNs have been particularly exciting for many applications because it introduces three key things. One, it's scale invariant. For a particular tumor that might be smaller or larger, it'll still be able to detect some of these things. Secondly, it's able to detect things that are in different positions of a particular image. But again, those things are already solved with the previous algorithms such as SIFT. What's the key difference here? Well, in 2000, the whole industry has moved towards something that is called learnable parameters, right? Instead of tweaking manual if-else statements, manual parameters in OpenCV libraries, people have been able to say, hey, there you go, this is a picture of a tumor, this is a picture of something else that is of a healthy population, go figure and go learn some of the parameters here. So I think this was kind of like a big major step with computer vision side leveraging CNNs such that things were learnable. But do people use CNN much these days? Well, you can see that with the recent Twitter beef between Elon and Yann LeCun, I don't personally think it's true that CNNs are dead. While Tesla might not be using CNNs standalone, I'm very sure convolutional nets are still a thing that people use these days. And I'll touch on some of the key technologies today that are still using it. So, but before we get there, it's important to talk about one often overlooked kind of big research that people are doing, which is K-shot detections. The industry for a while was trying to find ways whereby training large models wasn't going to be feasible for things that need to iterate quickly on, such as FMCG goods for planogram planning, things where you have large catalogs. It's no longer feasible to train a model every day as people add more and more new variety of data. So K-shot, zero-shot, one-shot learning has come into the scene, whereby an existing reference image using a query image set can now quickly see, okay, look, without further training, are we able to find different patterns here? And for those who might not know about K-shot, or zero-shot in this case, OpenAI ChatGPT is technically a form of zero-shot learning. You're not exactly providing new training data whenever you use it, but when you raise a particular topic, it's able to be answered for you. But after a while, we see many databases companies come up trying to solve the same exact problem with cataloging, which is if you have new images coming in, how do you detect whether it's something that's part of something you've already seen or something that's not? Well, vector searches come in as well, all right? People realize that it's much easier, instead of reading metadata of images and trying to understand different images or tag it, it's better to embed them as a particular vector and put it into different regions. Well, it's arguable that vector search is really a kind of just nearest neighbor algorithm, whereby if I have a picture of a cat, I put it into this corner. If I have a picture of a logo, I put it in another corner, and I'm just measuring the net distance between those groups and making a prediction. So we can see that some of these things, such as vectors, such as convolution nets, really come in to change some of the parts of the industry. But have we tried combining them? Absolutely. So with vision transformers, it's actually a nifty trick that combines a few methods in order to improve detection of things, right? If you look at a particular images compared to tokens in LLMs, the whole concept behind VITs has always been about converting small image patches, as you can see here, into little string tokens for the model to understand. And the big idea here is that why don't we just put it inside a transformer architecture and then make it learn it just like any other NLP application. But there's a big problem here, right? There's something a little wrong and missing in this particular image. Let me present something. So for example, we have a picture of Pedro the raccoon split into its individual patches of pictures as tokens, and we say, hey, that's Pedro. While the model is going to learn it, there's nothing inherently wrong about it. But if you were to shuffle something in a slightly different format, take for the one below, well, transformers, if you recall, they are generally invariant to the position of the tokens. So, but the picture below isn't technically Pedro. It's a jumbled up mosaic version of it. So the industry got creative, came in and changed VITs, or rather shipped VITs, with a few added features, right? But adding this thing called positional embeddings. So whenever you see vision transformers, you can realize it's kind of like a mix between the old NLP transformer architecture plus a few nifty tricks that the industry has employed in order to make sure that the models learn that, hey, this is going to be the corner, that's going to be in the bottom right, things like that. And then that's how we got up to VITs today. But again, the industry went ahead to add more and more layers on things, trying to cross-share and cross-breed different kind of architecture together to achieve better results. Well, in the latest Google I/O presentation, Polygamma, a multi-vision language model, was kind of announced. Vision language model isn't technically new, but it kind of presents almost the same idea, right? You will see same things as image encoder, a linear projection similar to that of a vector search, and different token concatenation about adding things such that the model itself have understanding of the different patches of where things are. And of course, you get your typical ChatGPT-like output. So you guys can actually go ahead and try it on Hugging Face, but we did it here for you. So if you were to ask a VLM pre-trained out of the box today, like Polygamma, you throw in a picture of that of MBS, you can ask it a bunch of things, really. You can ask it to segment out the building, and it's going to be able to give you a few tokens, again, as the output, of which it constitutes the kind of surrounding areas of where it's looking at, which is the red patches. You can ask, where is this photo taken? Well, I can answer it's Singapore. And you can also say, hey, can you caption this image? Well, it's going to give you the exact output that we have copy-pasted from the exact model itself here. So we start to see that computer vision itself has went from just simply identifying things, matching things, having small learnable parameters, to doing much more so that there's more utility in integrating things like that. But it's not without its different kind of downfalls. So if you look at another image on something that might be a bit more niched, say, for example, you want to use it for planogram planning, right? Can we use polygamma out of the box for it? Probably not, because if you look at this particular image, we ask it to segment out the guru cans, a kind of sports string. Well, it's not able to do it. That's not the right role for it. If you ask it, hey, can you detect the cans for us? Well, it's just going to answer you yes. Changing the temperature and the randomness of the model might not yield the answers that you want. And of course, asking it to count things that it might not have seen before in the general training set, such as counting the number of specific boxes, is going to get it wrong. So, but the industry isn't giving up just yet, because things like this are largely trainable. Provided in most open source models today are self-instructions of how you can train it and fine-tune it to things that you know and you want for your specific domain applications. So we have seen most of the workflows that big teams have employed is really around annotating new data, working with companies like SuperAI, many data annotation companies we see here today, fine-tuning the model, right? Again, learnable parameters are what's changing the industry today. And of course, evaluating it. There's many evaluation, LLM or kind of model evaluation frameworks out there for things like that. Applying guardrails for questions that customers can ask and things that customers can't ask. And of course, deployment, which constitutes about 25% of the startups I see out there around deploying and inferencing speeds. And of course, from there, people circle and label new data. So the paradigms has really shifted. And I think I'll leave you with this in terms of kind of where computer vision has been and will be. The previous paradigm, if you've seen, is around getting an input and algorithm, such as SIFT, such as finding out patches, things like that, things that were highly instructional, and there you go, you get output. But the current paradigm, things have changed. It's about putting in the input, saying that this is a training data, and putting an output and saying that that's something more of a output kind of data, which is the target variable that you want, and then get the model to learn it themselves. And of course, in production, you apply the same algorithm to get the results that you want. So what's the view on computer vision in the near-term future? Well, we believe that VLMs will see a large improvement in terms of new libraries, new checkpoint weights, and things that people will generally be able to achieve. And of course, architectural tricks for reducing memory footprints, things to power things such as Edge AI. Explainability, generalization, and of course, privacy-preserving techniques. Most public data that can be scraped have already been scraped, and most companies are trying to find proprietary data and private sources of data to train their own models, and that's where privacy-preserving techniques I've seen become a huge boom of things recently. So what does Datature do? Well, I think we try to address the exact same problems that we see here. Well, Datature is a company that provides developer tools so that companies can build never-seen-before models, such as cancer detection, niche manufacturing defect detection, so that the companies themselves fine-tune, label, and apply guardrails on their own models that they eventually own. And we do that through a simple way, which is by providing all the latest technologies in either security, privacy protections, and of course, fine-tuning methods, all within one platform itself. So if you're interested to learn more about computer vision, the wide history of it, and how we come here onto Vision Transformers today, we'll be happy to chat, and most of our teams are around the exhibition booth. So once again, thank you for your time, and I hope all of you will apply computer vision to your workflow some days. Thank you.